So today we're going to talk about the normal distribution. So far we have talked about discrete probability distributions, where we saw our just our probability distribution and then our specifically binomial probability distribution. And today we're going to start talking about continuous distributions, where we're looking at sort of a range of possible values instead of countable values. So we have that a normal distribution is very common and has certain characteristics. A normal distribution will always be, so it'll always be symmetric, bell-shaped, and centered about its mean. Normal distributions can differ from one another with respect to their center. Where is the distribution centered? And variation, so how much spread is there in the distribution? If a variable x follows a normal distribution, we write that x is, and there actually, I think we're missing an n, so x is approximately normally distributed with some mean and standard deviation. So just saying, with binomial distribution, it was a b. With normal distribution, it's an n. Now, example 1, it says each of the following are examples of normal distributions, but they have different centers and different spreads. So it's more of just an example of what we could see. So I'm going to draw my number line here. So I have maybe this here. I could have something this, and then something like this, right? So I have, some mean, we'll say A. My mean here would be B, and this would be mean C. So they all have a different mean. If we're thinking of the number line, the mean of A, this one here, this would have the smallest mean, and then the mean of C would be the largest mean. Now, they're approximately symmetric. I know maybe not exactly, just due to human error with my drawings, but the idea is they are symmetric, about the mean. So you could, if you, in theory, cut them in half, they'd be symmetric. Now, they are all normal distributions, but they definitely do look different, and that's where the spread comes in. So if I'm thinking of the standard deviation, the smallest one is going to be the one where the curve, is sort of more close together. So that's going to be the C. So my standard deviation of C would be less than the standard deviation of A, which would be less than the standard deviation of B, B, since it's the widest, would have the largest spread. So we do also look sort of both ways with what's the mean and then what's the spread of the data. Okay, so with that, let's take a look. And it says, how can we tell if a distribution is roughly normal? So there's sort of 4 things we can look at. The first thing says that most data values are clustered near the mean, giving this distribution a well-defined single peak. And we see that single peak with each of the ones from the last example, So second is that our data values are spread evenly around the mean, making the distribution symmetric. The third thing would say larger deviations from the mean become increasingly rare, producing tapering tails of the distribution. So our tails, so if I think of my tails, there's not as much maybe data over there because it's getting farther and farther the mean. Most of our data always with a normal distribution lies pretty close to the mean. And 4, it says individual data values result from a combination of many different factors, such as genetic and environmental factors. All right, so here's more of an official looking curve, a typical graph of a normal curve. We have a couple things that I'll highlight. So the first thing says the center or the highest point is at the population mean, So this piece here, that's the highest point, and that should be the mean of my distribution. The transition points, are called inflection points, are the places where the curve changes from a hill to a valley. The distance from the mean to the transition point is 1 standard deviation. So if you've taken calculus, you've heard of inflection points. Statistics actually, has to do a lot with calculus. We don't really talk about the calculus portion because that's not one of our requirements, but there is some calculus involved with statistics. So we call these inflection points, and it's just how the curve sort of changes. The area under the whole curve is exactly 1. So I'm just going to briefly sort of color this in. So what they're saying is everything underneath this curve, if we summed it all together, it would be 1. So that's what they're saying with that area. I'm going to erase that. And then it says, let's see, when a variable x has a normal distribution, we can describe that specific distribution using the notation, right? So x is the distribution is the normal distribution with this mean and the standard deviation. This is read as x is normally distributed with mean, mu, and standard deviation, right, sigma. So let's take a look at some 2 examples here. So example 2 says, which of the 2 variables below would you expect to have a normal or close to normal distribution? So if I think wages at a fast food restaurant where most workers earn minimum wage, right? So I'm just, well, we can think of like drawing a histogram, right? So here's my histogram. It says most earn the minimum wage, right? So most people, right, when they, right, start out sort of maybe something like this. But then you do have, right, the people that have been working there longer, the management, right? So those people are going to definitely make more. So there's going to be, you know, maybe some gap here. And so if I were thinking of the distribution, we looked at distributions in a previous chapter. This would look, there's some skewness involved, right? That most of the data lie to the left. Sort of our outliers are the ones, right, that are making more money are to the right. So we would say this is right skewed or skewed right. So we would not expect this to be really a normal distribution because it says most of the workers, right, earn minimum wage, which is sort of on the lower end, but there are some people that will make, you know, more money on the higher end. So then we have B, head circumferences for a random sample of 12-month-old infants. Okay, so if I think of infants in general, right, so here's my line, it actually follows a normal distribution for head circumference. You're going to see that the majority of infants, these 12-month-old infants, are going to have this head circumference. I don't know what it is, but whatever it is. And then there will be some that are lower than that, some that are higher than that. So my random sample of these head circumferences, if I took this random sample, would look something like this, where you'd have sort of that symmetric distribution, right? So this sort of bell curve. And so we would say this would be roughly a normal distribution. Normal distribution. And this usually with kids with height, weight, percentile, they talk about the percentiles, but a lot of times this is normally distributed. So these are just 2 examples, one where it wasn't normal, right, with that right skewed, and then one with a normal distribution.